2, 3. There you go.
Go ahead, yes.
Yes, good afternoon, everyone. It's my pleasure to welcome you to this final webinar of our series on the latest technologies throughout the cold chain and hot climates. These are publications and webinars series. They have been organized by the UNEP Ozone Action and the International Institute of Refrigeration as part of our ongoing effort to share knowledge and inform practice to advance the refrigeration sector, which is essential for human health and livelihoods while protecting the ozone layer, climate, and our environment. First, I would like to warmly thank UNEP Ozone Action for the crucial role it's playing for the success of the Montreal Protocol and on the ongoing work with Kigali Amendment, but also for the continuous and the true partnership with IIR. I would like also to thank all the participants for joining us in this webinar series and express my gratitude to the authors and our speakers, as well as the IR Scientific and Technical Council, UNEP experts for their valuable review and guidance in ensuring continuous quality and relevance of our publications. The refrigeration sector touches so many fields: agriculture, health, energy, technology, humans, animal well-being, and of course the climate. And as no country can navigate these challenges alone, and given that these issues are cross-borders, achieving real progress requires first a strong coordination at the national level, and then a collaboration between countries and organizations. This includes exchanging knowledge, connecting experts, and building bridges between science, industry, and policy. And by working together in this way, we can promote practices that reduce refrigeration demand, adopt energy-efficient equipment, and transition to clean, low GWP refrigerants, as we are doing now. The IAR has long acted as such a bridge, bringing science everywhere, making it accessible, and translating it into practical, evidence-based recommendations for countries. We also bring the realities of policy evolution and industry practice back to scientists, helping guiding their next innovations and research focus areas. In doing so, we ensure that science and technology remain responsive to real-world needs, while supporting industry in adopting sustainable, efficient, and climate-friendly solutions. This work is made possible thanks to the long-standing and valuable partnership between UNEP Ozone Action and IIR, which is a good reflection of this spirit and continues to advance the knowledge and practice in the refrigeration field globally. To all countries, experts, stakeholders, I invite you to join this noble collaborative effort to become part of the IR family and join helping us continue advancing the refrigeration sector through advanced research, better informed policymakers, and engaged industry players. With that, I wish you all an insightful and productive webinar. I would like you to note that there is an English to French translation, which is available by clicking the globe button in the toolbar. Thank you very much, and over to you, Suhir.
Thank you, Yusuf. Over to you, Misha. Moderation.
Thank you very much. Thank you very much, Yusir, for setting the stage and emphasizing the importance of innovation in refrigerated transport. And before we begin, here is today's agenda. So we are going to have today two keynote presentations on refrigerated transport challenges and advanced solutions. These two presentations will be followed by a live question and answer session, which of course will be organized, and please use the question and answer box for your inputs, questions, comments, and this is a chat for all for everyone. So Nella will assist us kindly throughout this session. So we move to the keynote one, which is and I'm very much pleased to introduce Silvia Minetto, senior researcher at CNR and president of IIR Commission D2, who will speak about road transport refrigeration challenges and opportunities in hot climates, including key technologies and energy efficiency solutions. Silvia, the floor is yours, please.
Thanks, Misha, for the nice introduction. Then I'm going to start with a very brief overview on transport refrigeration. Transport refrigeration is an essential link in the cold chain, as it guarantees that product is kept at the right temperature throughout its life, while keeping the fluctuations under control. IAR estimated that the global fleet in 2024 was close to 6 million vehicles. And there are different projections with improved cold chain scenarios that project this number up to 11 million vehicles in 2050. And the important thing is that the increase will be mainly concentrated in the global south. So this is the first key information for this overview. Then we have asked ourselves what hot areas are. And so we have gone to the Copper-Geigen classification. And in this map, you can see the magenta and red areas, which represent the tropical in magenta and the desertic and semi-desertic areas. We have crossed this map with the logistic performance index provided by the World Bank, which scores the logistic infrastructures. And you can see actually different shadows of these colors, magenta and red. But what comes out from this analysis is the fact that hot areas often lack logistic infrastructures. The gray countries that you can see in the map are countries which are included in the hot areas, but for which we don't have this LPI value. This is one side of the coin, but the other side of the coin is the fact that heat waves are also affecting areas with developed infrastructures and also areas where the climate has always been considered to be mild. And this makes the need for sustainable solution for transport refrigeration a global challenge. So it's not only a matter of global south, it's a matter also of facing the heat waves that are affecting the countries where the infrastructures are developed. So I'm playing with the Okay, this is the sketch of this is the basic elements of a transport vehicle. So we have traction, which is moving everything around, and we have the insulated box, which is the minimum requirement for talking about transport under controlled temperature. And then we have a refrigerating unit, which is keeping the temperature inside at the set value, or even a thermal energy storage system, which means a material which is frozen or liquefied in advance and then keeps the temperature inside at the desired value for a certain time. And then overall, we have practice and logistics. There are some loads that are affecting the box, and these loads are the pull down, because we can't forget that we are within the cold chain. It means that when we load our box, we need to have already the right temperature inside, because we don't have to have fluctuations in the product temperature. And then we have conduction through the walls. We have air infiltration during door opening, because every time that we open the doors of the box, then the cold air goes out and hot and humid air comes in and replaces in a very, very short time all the air which was already cold inside the box. And then we have also solar radiation. So the first question is, what happens when temperature increases from 30 to 50? We can first talk about the conduction heat load. So what comes from the walls of the box when the box is closed. And this is typical of, for example, of long distance transportation. The capability, the insulation capability of the box is typically described by the K value. K is the symbol which is used in the ATP, which is the Agreement on the International Transport of Perishable Foodstuff. But this is also identified with U widely in the literature. It's the overall heat transfer coefficient. The conduction heat load depends from the temperature difference between outside and inside. So if we move from 30 to 50 degrees, we can see that the thermal load increases by, in the worst case, which is the case in which the box is at 0 degrees, it increases by near 70%. Then the second load is that we are considering is the air infiltration load. When we open the doors, so the hot and humid air comes in, and then when we close the doors again, we have to pull down this air to the initial set point. In this case, there is not only temperature that we need to consider, but also humidity. And this is why we have distinguished the desertic climate on the left and the tropical climate on the right. And we have made some assumptions in terms of combination of temperature and humidity for each of the climates, of these climatic conditions. And our reference is 30°C and 40% relative humidity. So if we stay on the left graph, in a desertic climate, there is actually an increase in the air infiltration load if we move from 30 to 50 degrees, but it's quite limited, and this is because the air is very dry. But if we go to a tropical climate, and this is described in the right graph, then the situation can become very complicated, because if we move from 30 degrees to 50 degrees, with respect to the design condition, which was 30 degrees, 40% relative humidity, considering that at 50, we have assumed 45% relative humidity, we have an increase in the thermal load, which can be as high as 180%, which is a very huge increase in the thermal load. This is one point. So when the temperature outside increases and the humidity increases, we have an increase in the cooling demand of the unit to keep the temperature inside. But the other big issue is related to the fact that typically we have a vapor compression cycle, and the vapor compression cycle is working towards the external environment. And if the temperature outside increases, then the cooling capacity that compressor and the refrigerating unit itself is going to deliver is much lower. This graph is just a trend, and it represents what happens to the cooling capacity of a compressor. We selected a commercially available R404A compressor from a manufacturer catalog. The cooling capacity moving from 30 to 50 goes down by 44% if we work at -20. Of course, these numbers are related to the compressor that we have selected, but the trend is very similar for all compressors and refrigerants. So what happens if we combine these two challenges? On one side, we have an increased thermal load. On the other side, we have a decreased cooling capacity of the unit. What happens is that, for example, when we have to pull down the air after door opening, we have to pull down the air again to the set point, the system has to work longer with respect to the reference situation. And on the left hand, we have the situation in the desertic climate. So there is an increase in the pull down time, which can be around 100%. It means that it takes the double of the time to pull down again the internal air volume with respect to the design point. But in the case of the tropical climate, which is on the right hand, the situation can become really dramatic, because it can take up to 450% longer than in the reference case to pull down the system to the initial temperature. And this means that if the unit is not correctly sized, the system might not be able to reach again the set point, and this can result in a higher internal temperature and in a large fluctuation of the product temperature. So these are the challenges, but we have also some, of course, opportunities to face. So how to face this problem? So let's start from the box, which is the starting point of our analysis. So as I said, the conduction through the walls is described by the overall heat transfer coefficient, and this coefficient drives the heat load for long distance transportation. So for all these situations in which we load our system at the depot and then we unload it when it is arrived to the final destination. ATP sets some values, so some maximum values for the K according to the type of goods that we are transporting. And these are already a good indication for the construction of our box. But we know that with the present construction of sandwich panels and with proper design and construction, we can achieve K values as low as 0.3 watt square meter Kelvin or even lower. There are also different techniques like panels including VIP, which have excellent properties, even though there are still some issues that need to be solved, like production, cost, maintenance. I've not mentioned the radiation so far because it is not relevant when the system is moving. So when the truck is moving, there is a balance between the radiation load and the external convection, which is removing the excess heat. But radiation can become a challenge during parking and queuing. So a clean white surface needs to be adopted because it has been demonstrated that the black surface can increase the load by more than 50%. And finally, we have infiltration. So there are different systems that can be applied. There are active systems like air curtains. Air curtains, of course, use energy. So we need to work with a sort of trade-off between the heat load that we can prevent and the energy that we are spending to keep these air curtains. And also plastic strips, which are, on the other hand, some passive components. And both of them can reduce significantly infiltration and consequently the fluctuation in temperature of the product. So, okay. No, I'm sorry, but okay. So I'm sorry, okay. So we have to prefer a design which minimizes the K value. It's not only a matter of which panels we adopt, it's also the construction of the box and, for example, the location of the doors, the number of the doors, and so on. And we have to choose a white surface. And then there is good practice, which is very, very important. So the box must be maintained. The surface, external surface must be kept clean. We have, for example, some good sense, common sense practice like park in the shadow, load under controlled environment, minimize door opening, I mean in number and time, and use curtains. The second element we can play with is the refrigeration unit. So undersizing can really result in long recovery time and inability to reach set point. We have seen the examples in the tropical climate. So it's important to size the unit large enough to handle the thermal load that we are expecting. On the other hand, oversizing is not the solution to all the problems because oversizing can introduce losses due to cycling. Because we are not only interested in providing the right cooling capacity, but we must do it in a sustainable way. So it's also important to minimize the energy consumption. And coefficient of performance is widely used in stationary refrigerant and can also be a good parameter to evaluate and compare different units at fixed working points, like the design point, for example. We all know that COP thermodynamically depends on the combination of cycle and refrigerant, but to achieve this COP, we must implement efficiently and properly sized components. So the type of components and the sizing of the components, like heat exchangers, is important to achieve a good COP. And electrical connection between the driveline and the compressor and the use of an inverter can enhance efficiency. And it's also important to point out, Antonio will go deeply into this, that electrical driven compressors allow for integration with renewables, which can contribute to the energy balance of the system. Okay. And options for sustainable transport are also very much related to the choice of the refrigerant, because the transport refrigeration systems are subject to relevant leakages. So every year we can lose a relevant amount of the charge of the system itself. Of course, there is not a fixed number for this, but it depends very much on which system we are using, which type of installation, and how the system is maintained. But the important thing is that present refrigerant are F-gases, and in the literature, it is widely recognized that refrigerant emissions can account up to 20% of the total greenhouse gases emissions of the refrigerating unit. On the other hand, we also know that refrigerated vehicles are long-term investments. So the choice that we do today will have an impact for a long time, many years. So sustainable refrigerant choices must be done today. And when I say sustainable, I mean that refrigerants need to have a negligible or null GWP, but also be safe towards the ecosystem. So no PFAS. And solutions with natural refrigerants are available or they are coming. For example, hydrocarbons have demonstrated higher COP versus the reference system, also up to 50 C ambient temperature for both fresh and frozen products. And self-contained units with a reduced charge and secondary loop are already available on the market. CO2 has been demonstrated for containers and it is under demonstration for road transport. So coming to conclusions, high ambient temperature, we have seen that high ambient temperature significantly increases the thermal load, and there is also a big role played by humidity, and it negatively affects the performances of the refrigerating unit. We have seen that low overall heat transfer coefficient can be achieved with sandwich panels and proper construction techniques. Proper sizing of the unit, the use of efficient components, electrical connection to the driveline can reduce energy consumption and emissions. We do have technology for applying natural refrigerant, and this technology is available also for hot climates. It's a matter of finding the most suitable solution for each application. So long distance, short distance, big units or small units, and frozen or fresh product transportation. And the choice, as I said, must be done today because the life of this kind of systems is quite long. So what we do today will have an impact in the future. And finally, maintenance and good practice can really make the difference. So that's all on my side. Thank you for your attention.
Thank you very much, Silvia, for those valuable insights on challenges in hot climates and energy efficiency solutions, which are connected with road transport refrigeration. Excellent. We are on time, so we are moving to the keynote speaker 2. On the second keynote, we'll focus on advanced solutions and research insights, including case studies and performance metrics. Please welcome Antonio Rossetti, researcher at CNR and Secretary of IIR Commission D2. So Antonio, over to you, please.
Thank you very much, and hope you can hear me well. So this presentation is divided in two, and before everything, a small introduction to the topic. I want to start with this kind of layout just because every kind of solution has to be discussed in its specific application. So we have first to have a look on the cold chain transport and discuss what cold chain transport is. And a way to make subset of it is a way of dividing the kind of trucks we are using. So we can divide the light commercial vehicle, medium and heavy commercial vehicle, semi-trailer. Then we have intermodal transport, which is not a topic for today, but just to keep in mind is also there. And then it's not yet finished because we can then split the set again. When we discuss what we are transporting, we have frozen goods, we have chilled goods, and we are plenty also of goods that are not even chilled. They are transported at positive temperature, maybe not for food safety, but for food quality, such as fruit and vegetables. And they also have other prescription in humidity and temperature than the other, but it's not yet finished because we can also divide the sector when we look at how the goods are transported, where they are transported. We go from the long-haul delivery, international transport, to the last-mile delivery. And the way we operate the truck, the way we handle the goods, it changed the way the equipment has to interact with the thermal loads. And this is not yet finished to picture the complexity of the sector. This is not meant to be a strictly and comprehensive taxonomy of the sector, just to give some idea, but it's not yet finished because we have to add on top of it also infrastructure, because transport rely on infrastructure, and having some infrastructure or not having them, the lack of them, can strongly imply different way of using your cooling equipment. And also climatic condition strongly affect the performance and the choice you do when designing the refrigeration equipment. So, given this premise, it's not possible to present you solution for everything. So I will just dig into details of two specific solutions we have developed in a project called ENAF. It is an European project funded by the EU Union, in which we try to present sustainable alternatives for transport. One is called Fresh and Green Delivery, and it is a vapor compression cycle with CO2 as a refrigerant, designed for a light commercial vehicle for transport of fresh goods. And everything is electric here. And we have also solar panel on the top of the truck. And the other one is a different approach to refrigerated transport. It regards frozen goods, and it is a thermal energy storage approach. So we have eutectic materials that is frozen using a propane refrigeration unit, and the system do not apply to the truck as a whole, but just to a transportable box. And the box itself is then transported using a truck. There are two different points of view, but they are not pictured in the whole picture, just focusing on two applications. So let's go on the first one. This is a nice picture showing you how it's supposed to work. We have a battery pack powering the refrigeration unit, and we have solar panel aiding the battery. It's not relying only on solar panel. It's expected to be powered through plug by the electrical grid, but solar panel can contribute to the energy balance of the unit. And then we have the refrigerant unit with natural working fluid, in this case CO2. We started by taking as a reference the stationary application for commercial refrigeration with ejector, and the challenge here was to apply this concept to a small power application, just 6 kilowatts of cooling power at standard condition, and make everything work. So make the ejector works for such a low capacity, and the control system in order to be able to manage the high pressure and the ejector itself. So we started with a proof of concept in this stationary application, and we got good results, I would say, in terms of COP and cooling capacity. And when you compare the red line and the green line, you can see that the red line refers to the ejector configuration. And so ejector is in some way a complexity, but is paying for this complexity because it can increase the performance both in COP and cooling capacity for high ambient temperature, so for temperature higher than 30 degrees Celsius. Then with this positive feedback from the stationary unit, we moved to a more engineered solution for the prototype. And thanks to other partner in the consortium, we built this prototype. We had this ejector that has been designed using our data, the one that we defined before. And that's the final results at the end. So we have a totally zero emission vehicle. It is an electrical vehicle with the electrical powered cooling unit is running on CO2. And this one has been coupled with the acquisition remote monitoring system, because we want now to collect the performance of this unit in a real world application. And this is the first one. Then we move to the second one, which is a thermal energy storage box. You have the box, we have thermal energy storage material inside it, and the cooling unit is electrically driven. You can plug it in the electrical grid, and this unit solidify the thermal energy storage material, the eutectic material. And then this material can keep the temperature inside the box below a threshold for many hours. And this is the expected application of this box. You can, after charging it, after solidifying the thermal energy storage, you can load refrigerated goods, and transport by means of a non-specialized transport truck. And the good idea is that you can also couple this one with transport of non-frozen goods. And then when you arrive at the final destination, you can unload the frozen goods, the temperature-controlled goods, and also the normal stuff you're bringing with you. And another option that we forecast for this kind of application is an emergency scenario application, because you can transport this one by means of off-road vehicles, for example, and it can work as a temporary storage, just plugging it to an electrical grid. And if the electrical grid is not reliable, that's sometimes it happens during an emergency scenario, then the thermal energy storage can help you in keeping the temperature below the threshold. Here, the challenge was very different than the previous one because technically, eutectic materials are a mature technology. So the idea was to demonstrate the competitiveness of a natural-based solution and integrate unconventional solution for housing the eutectic materials. Eutectic materials was stored here in tubes. That has many advantages. One that is that the refrigerant tube is external, so it can more easily comply with safety standards when you have a flammable refrigerant, because you can inspect this one and you don't have connection or welding inside the box. And then it can also exchange by convection and radiation to the walls and the goods inside this box. And this, again, if you use this one as a temporary storage, this can be a positive effect. Regarding the propane unit, it was a quite standard unit, nothing very interesting here. But that's the end of the work. We demonstrated we can do this one, and the autonomy, so the time this can keep the temperature below threshold, was in line with expectation. And the system proved also, in compared to the baseline, that was a synthetic unit, a better energy ratio. So the unit of energy spent can give you more time below threshold, more time of controlled temperature. And now that I have presented you this solution in general terms, some numbers, some projection of how we expect this kind of solution can reduce emission. So these are numbers based on a lot of hypotheses. So we thought about a standard usage for this kind of unit that is a delivery emission. We fixed the ambient reference temperature and condition, and we ended up with these numbers. So you can see in gray, you have the reference bar for the emission of a standard synthetic unit, and the yellow one is the relative emission you can get with this kind of sustainable solution. It is 25% in case of the light commercial vehicle and 49% in case of the eutectic one. And one important thing I would like you to focus your attention is that efficiency is just a small part of the advantage. We are saving just 9% and 5%, but the huge advantage in terms of emission is the lack of an actual impact of leakage emissions. Because when we use natural, we have still leakages, but they do not impact in terms of CO2 equivalent because conversion factor is GWP is very, very small. And then another huge contribution here, this minus 44%, come from the electrification of the refrigerant unit in the light commercial vehicle, because the reference unit uses a diesel engine to power the unit, but electrical grid has a much lower conventional factor that diesel engine, and this can bring to a huge saving in emission in the overall. And then some research insight. This is the second part of the presentation. And again, I'm going through this slide to say it again that this is a quite complex and divided sector. So it's very difficult to have a universal truth in this context. So I will try to share with you some insight, but everything has to be again discussed when the specific configuration is discussed, so specific application. Natural refrigerant, the first topics. So I would say that CO2 and hydrocarbons can be a viable option for the transport, but we need more research in the components, so compressor, valve, heat exchanger, to be optimized for transport. We need careful selection. We need to tailor the design in order to get good performance. It's not about just taking whatever is into the market, putting them together and expect it to work. It doesn't work this way. We need high performance designing phase to get good performances. And we also to raise the trust of all the stakeholders involved, from manufacturers to end users to the network and the maintenance, because we have to raise this awareness and build trust on this kind of solution. Another important point is that efficiency is not the full story. As I showed you before in numbers, naturals can give you an advantage in efficiency, but the point is that the unmatched benefit is the fact that we don't have anything we cannot predict about natural substances. There's no drawback, no unforeseen drawback in a short term or long term from naturals. And this is the key point. Last, we need a balanced approach between highly specific specialization of units, so one specific unit for each application, and the other approach, which is universal solution, just one solution for all the approaches. They doesn't work because we have to make it a reasonable complexity toward the market. So we have to group application and try to find where this compromise lay. And in this compromise is not only technical, has also to consider infrastructure, socio-economical and educational boundaries, and logistics. In terms of energy source and electrification, battery power transport refrigeration units can fulfill requirements for zero emission zones and noise regulated areas, but weight is a point. So we have to think about the weight we are adding to the vehicle and see this one in a life cycle assessment perspective to see if this is actually an improvement or not in the vehicle balance. And solar panels, on the other side, I would say they are lightweighted elements that can complement the energy balance of the refrigeration unit. And as the thermal loads and the solar source, they are quite correlated, we can take advantage of solar panel also with very small battery capacity, because the energy we are producing, probably we are using it in a real time because we have thermal loads on the system when we have the sun. E-axle on the other side are also an option, but they are usually considering semi-trailers to make the vehicle work as a mild hybrid solution. But let's say that semi-trailer usually drive in highway where you don't have braking energy to recover. You're usually driving at cruise speed, so has to be discussed in every specific application. If you expect your vehicle not to brake a lot, maybe you don't get much from e-axle. And again, just a focus on diesel engines used to power the cooling units. The non-road mobile machinery has a lot of emission in terms of pollutants, so PM and NOx, and we have to take care also for this in terms of local pollution. Thermal energy storage is the last point on this presentation. It's something that right now is present in a very small share of the market, but has some key features that can be interesting on the overall, because it can be employed to fulfill the request for cooling transport by presenting centralized solutions. So we can have just one centralized cooling plant providing the cooling for many vehicles. And this has a positive scale effect on performances, simplify the maintenance of the system, and for sure a clear interaction with solar panels and the electrical grids as every stationary application. We are moving the cooling unit from a transport point of view to a stationary application. Zero energy demand during transport, that's a positive point. And also if you transport the refrigeration unit, it can work as a temporary storage. But I think something we have still to research is the sustainability of materials. So we have to look forward for sustainable, possibly natural thermally restored material to support the sustainability of this kind of solution. Thank you.
Thank you very much, Antonio, for sharing practical applications and the lessons learned on cold chain transport sector. That's great. We have now about 15 minutes to open the floor for questions. Please, I would like to remind everybody that please submit the questions via the question and answer box and not through the chat box. We will address as many as possible in the time what we have. It's basically 15 minutes. So I will start with the first question, which is what are the main barriers preventing the development and widespread adoption of the small capacity absorption refrigeration systems, 1.5 kilowatts, in developing countries such as Senegal? So I don't know who will respond, Antonio or Silvia, please.
I can try to take it. Probably I don't have the final answer to this. The main challenges, to my knowledge, the main challenges of absorption systems, refrigeration system for transport, are related to the source, to the energy source, which is always be considered the engine, and the temperature of the exhaust gas from the engine is decreasing due to the increasing efficiency of the motors. And for example, in our regions, we are thinking about alternatives to internal combustion engines. So this is probably one of the reasons why there is not too much effort, to my knowledge, on this. And in the literature, we can find different works where they explain that it is typically necessary to have an alternative source. So in parallel with the use of exhaust gas, it is also necessary to have an alternative source to cope with this fluctuation of the available temperature source, and also to provide cooling during the when the truck is not moving, so the engine is not on. So I think these are and when you need two systems, then things becomes complicated, especially for small systems where cost and space is an issue. I hope I have given at least some points to think about.
Thank you very much, Silvia. Antonio, would you like to add, or we continue with other questions?
I don't think I have nothing to add to what Silvia already told. So thank you.
Thank you. Thank you. We continue. There, just for information, that there is a chat box. I again remind everybody that you can put the question and answers chat box the questions. So let me move to the next. Yes, please.
No, because I was speaking, but I was muted. If I can add a comment from the absorption cycle perspective, not from the transport. No, this is only, I mean, the absorption systems, they use more energy than the classical vapor compression system. And then it may be challenging because of the limited waste energy fuel available. But also these are like large capacity systems. They are big. And then there are some, space constraints as well when it comes to transport.
Thank you very much, Yusir. This is helpful, and we continue. Are these company or products in the market that uses thermal energy storages?
Yes.
Antonio?
Yes. Okay. No. Okay. Yes, for sure. You find them when looking for eutectic system. They are the materials, the thermal energy storage are eutectic material called so, and they are usually used for low temperature application. So yeah, they are usually applied for ice cream, I would say, or other frozen goods. but they are available on the market.
Okay, thank you for that. We continue.
Thermal
move
energy
on.
storage, just to say, thermal energy storage
Yeah.
is a more academical term, let's say, and euthetic is more close to the industrial terminology.
Okay. There are basically two questions which we can connect with each other. How far this solution you presented from a real application on the roads, and could we use alternative refrigerants in transport refrigeration system replacement of CO2?
Okay, so I will start with the first one. The idea of this demonstrator is to demonstrate them on the field. So in a real application, so with an actual logistic partner that apply them in real world. And the actual offer of this kind of solution into the market, I don't have an answer on this because I'm following let's say the project on the research side of it and not on the economic side. But I think that this kind of solution can be brought to maturity with the research and the interest of a company working in this. And we have some kind of solution based on naturals actually on the market. Regarding the second part, so the one on CO2, I'm not sure I get the idea of what we are, where the question is, Silvia.
Now, that's also my point. So I'm not sure I have got it correctly. What are the alternative refrigerants used in transport system replacements of CO2? I'm not sure I got the question correctly. So
maybe because there are a couple of questions about CO2. So, for example, is CO2 viable for tropical and hot climates?
okay, so the compliance of CO2 with a hot climate, this is a good question in the sense that it is widely recognized that when the temperature outside is very high, the simple cycle working with the CO2 is not the most efficient one. And this is why Antonio has presented that system which adopts the ejector, and he has demonstrated that COP also at high ambient, even if not at extreme temperature, because I can't remember, Antonio, it was 40 degrees, if I'm not wrong.
Yes.
And in that case, it was the maximum temperature at which it was tested. I think that even though it is not probably it will not be the most widespread solution in very hot climates. It depends, the success depends on how much effort we will put on that, because solutions, for example, for stationary refrigeration with the CO2 have been found also with carbon dioxide. So it's a matter of commitment towards research and development of these systems. Of course, it is clear that hydrocarbons are better suited for high temperature.
Okay, let me see if let me see other questions in the chat, in the question and answer box. Just a moment, please. Okay, I can't see. Oh, there is one question about R74 with ejector is heavy system, high cost with high probability for leakage. R290 direct evaporating system with safety systems at highest efficiency, reasonable price. So maybe you can provide more insights on this. Antonio or Silvia, please.
Silvia, you want to get lead?
Yeah, yes, I can say a few words and then okay, about weight is definitely a challenge in transport refrigeration. And so simple system and light system are really the goal of the research and development activity. But it's not necessarily that an ejector-based system is heavy and complex. For example, the one that Antonio presented was very, I mean, linear and with very few components and with I mean, no control on the ejector itself, so it was a static component. About hydrocarbons, yes, they are systems available and they are suitable also for hot climate. So, and I would also add that there is also a new standard to for risk assessment in transport refrigeration with flammable refrigerants. So everything is there. So yes.
Okay, and I will add something regarding yes, the CO2 and the choice between, let's say, CO2 or hydrocarbons. I will say that an interesting point of view on this, we can have a different perspective if we look in the automotive sector. They are, I think, more deeply in research than refrigeration, and they are now trying to solve a solution for air conditioning and heat pump into passenger cars. And they are developing different companies, different strategies. Someone is working with hydrocarbons, someone with CO2, and they are also developing new generation of components, lightweighted and reliable for the pressure and all the features that are needed in transport, so vibration and so probably looking forward, the point is that we need components developed, optimized for them. They are technically doable. We can do them for sure. If we just copy the components from stationary application, we will end up in something that is so heavy that you cannot transport it. But there's a way of doing things lighter and more efficient, more aligned with the transport requirements. And regarding CO2 and hydrocarbons, probably they will both play a role, probably in different application, different size. If I think about a very high power unit, it can be for sure doable with hydrocarbons, but maybe for some reason of safety, or maybe you have to store the truck in a confined area and then you prefer CO2. Or maybe in a smaller application, you prefer lightweight, easiest components, and you go for hydrocarbons. I'm not sure about this. I don't think it's a rigid rules, but the point is that competitiveness between these two kinds of solution is positive. We will end up with the best of the two in their better context.
Thank you very much, Antonio. To continue, there is a very interesting question. Why did you choose R744 for the refrigeration unit for the vehicles and not a direct evaporating system with R290?
Okay. Tanya, do you want to answer or?
Okay, just because I think we want to research everything, so it was not just this one and not the other one. We had to start from something. So we defined the option at the beginning, and then we defined to test hydrocarbons on the thermal energy storage side and CO2 on the other vapor compression cycle. That is not meant that is not feasible, or we do not believe that it could be done in another way. We just wanted to test how small we can shrink an ejector cycle for CO2. I think that the challenge was this one.
Because we have just 5 minutes, I will try to maybe 2 questions more. One question is, what's wrong with the cascade systems? They are in the market already.
Yes, there is nothing wrong with the cascade system in itself, but I think that it is important to keep the complexity and the weight and the size of the system limited. This is a challenge for transport, which is not always present in a stationary, where maybe you have more space and you don't care too much about weight. So it's a matter of keeping the system compact and having, a light system. So nothing against in principle, and it's not a cascade. But it's a double loop system. For example, there is a double loop system available in the market, where you have on the cooling system, you have propylene, not propane, and on the secondary, it's a CO2 in a thermosiphon cycle. So there is a possibility to do 2 cycles. I would say that keeping the weight low and probably 2 compressors are not, in this direction is an issue.
Thank you very much, Silvia. Maybe last question for today. When hydrocarbons will be used in transport refrigeration, is there a need of any specific safety measures? Is there any such guidelines available? This is a very good question.
Yeah, yes, there is a standard, EN standard, so a European standard. As far as I know, there is a European standard on this. So driving the risk assessment for flammable refrigerants in transport refrigeration. I'm not aware. Maybe Antonio can complement this answer, as it was involved.
Not on a specific term, but just to say that every time I hear this one, I'm quite puzzled by the fact that transport sector has always been facing flammable fuels and also in high pressure flammable fluids. So I think that technically, for sure, it's something we have to care about, but I think it's something that we can solve technically, the problem of flammability. Furthermore, in transport, where we are used to have natural gas, for example, for driving the vehicle, or a lot of diesel, or we have liquefied natural gas application right now. So I think that with the right effort, there's a way to solve this problem. So just to be careful and to dare enough to solve them.
Okay, thank you very much with this. And I would like to say that there are much more, there is a very lovely discussion in the chat box. So if people want to consult with the kind of comments and reaction of the people, you can read in the webinar chat box. With this, we conclude, and I would like to invite Jim Curlin, head of the UNEP Ozone Action, to share closing remarks and next steps. Please, Jim, over to you.
Great, thank you, Misha. And I'd like to give a big thank you to our excellent speakers, Silvia and Antonio, and to our IIR colleagues, and to all of you 150 participants for joining today's webinar. So as we've heard, we focused on the impact of high ambient temperatures and humidity on refrigerated transport, and we learned about a range of solutions. And this ranges from better insulation, using white-colored outside walls for the lorries, introducing efficient refrigeration units, thermal energy storage, integration with renewables, and the adoption of natural low GWP refrigerants as long-term sustainable choices. So all of these measures are essential to ensure food safety, to reduce emissions, and to strengthen climate resilience. Now, regarding low GWP natural refrigerants, we just heard from Silvia and Antonio that while all of these are technically very good solutions, still some research, development, and commercialization work is required for them to be used in high ambient temperature and humid conditions. And those conditions are, as we've heard, are really challenging on refrigeration systems. It also takes time for these new technologies to spread to all of the developing countries, which are often the technology takers, and they're at the end of the distribution chain. In general, transport refrigeration is often an overlooked sector in developing countries, and very few countries give it attention under their HCFC phase-out management plans, the HPMPs, or under their Kigali implementation plans, their KIPs. And transport refrigeration is not as prominent as, say, domestic or commercial refrigeration. And yet transport refrigeration is absolutely essential for preserving the food supply, and the agriculture and food sectors depend upon it for their economic success. Transport refrigeration is really the thread that binds the food cold chain together, and it literally covers not only the first mile from the farm, but also the middle mile to the storehouse and the market, and the last mile to the consumer. So making informed decisions about technology choices to promote the adoption of low GWP and energy efficient technologies is very important for the new refrigerated vehicles, the newly purchased ones. But it is equally important to maintain energy efficiency and to reduce leaks in the existing fleets of lorries, trucks, and refrigerated containers. So I see there's a lot of national ozone officers online. You may wish to consider a two-pronged approach, particularly under your KIPs. So first, you want to promote the adoption of the new technologies in the transport refrigeration sector. But second, you may want to consider having a targeted program to properly service and maintain the existing refrigerated transport fleets so that you reduce emissions. And I wish to note that the transport refrigeration systems are usually not serviced by the same technicians who repair domestic air conditioning and refrigeration. So transport refrigeration merits special attention. Okay, so today's webinar concludes our series about the four cold chain technology briefs. And as we heard from the beginning, developed through our strong collaboration with the International Institute of Refrigeration. And this initiative began at the 37th meeting of the parties of the Montreal Protocol, a side event, which focused on walk-in cold rooms in Article 5 countries. And it was followed by webinars on fishing vessel applications, and another on commercial, professional, and domestic refrigeration. And finally, today's session on refrigerated transport. So together, these resources provide practical guidance for policymakers and industry to adopt low GWP, energy-efficient solutions across different parts of the cold chain. I wish to express our deep appreciation to IIR, to Yoser and her team for their technical leadership and their partnership, and to all of the experts who contributed to these briefs, including Sylvia and Antonio. These resources they're not just technical documents. They're meant to be practical tools to build the capacity of national ozone officers so that they can engage in informed discussions with their ministries and refrigeration stakeholders at the national level. And we hope that they will facilitate a better integration of cold chain considerations into your Kigali implementation plans. And basically to help you make strategic decisions on refrigerant choices, energy efficiency, and infrastructure development. So I encourage you to please download the technology briefs, listen to the recordings of the various webinars if you didn't join the other ones, and to share them widely with your interested national stakeholders. And join us together in advancing a cold chain that connects climate action with food security and economic growth. And with that, thank you very much for your attendance, and over to IIR for any other closing. So thank you.
Thank you very much, Jim. Thank you very much for your closing remarks. And of course, we encourage everybody to explore the IR UNEP cold chain technology briefs, as you mentioned, and of course, stay connected for upcoming initiatives. Thank you very much, Antonio and Sylvia, for excellent presentations. Yusir and Nel for great support. And thank you again for every participant for joining us today. So have a great morning, afternoon, evening, and see you next time.
Thank you.
Thank you.
Thank you, everyone.
Thank you.
Thank you.
Thank you.
Thank you.